Let's look at methane. Methane is CH4. If we look at the valence electrons for carbon and the valence electrons for hydrogen, here's hydrogen, here's carbon. Carbon has 4 valence electrons, and it'll be 2s2, 2p2. So we have 2 half-filled p orbitals. And so what valence bond theory is going to say is, well, one hydrogen can overlap with this p orbital, and another hydrogen can overlap with that p orbital. And it would predict that we have something like this, where the formula would be CH2 with a bond angle of 90 degrees. But what we observe actually happening is that carbon and hydrogen form methane, and there's actually 4 hydrogens that bond to carbon, and the angle's 109.5. So there's something missing from what I've told you so far, right? An additional concept is needed. And that additional concept is hybridization. The orbitals in the molecule are not necessarily the same as the orbitals in the individual atom. When those 2 atoms come together and interact with each other, that interaction can affect the orbitals. It can change the orbitals. Hybridization is a mathematical procedure in which standard atomic orbitals are combined to form hybrid orbitals. So you can think of it a little as averaging. Remember, the orbitals were described by mathematical equations called wave functions. And so you can take those wave functions and combine them to get hybridized orbitals. The details of that are way beyond the scope of this course, so we're not going to talk about them. These hybrid orbitals correspond more closely to how the electrons are actually distributed in molecules. They're still localized on the atoms, though, but their shapes and energies are going to be a little different than the standard orbitals. So let's look at how this happens. The hybrid orbitals are going to minimize the energy of the molecule by maximizing the amount of overlap. So we're going to get more overlap, because more overlap is going to cause it to be more stable. One of the ways that this is accomplished is that the electron density, or the electron probability density, gets more concentrated on one side of the atom than the other. If you remember the p orbitals, they have lobes that are equal sizes on each side. And so half of the electron density is on one side of the atom and half is on the other. When we hybridize, it gets lopsided, and we have a big lobe on one side and a small lobe on the other. And so we can get more overlap, and it gets a more stable molecule. Now, that hybridization requires energy. It's not going to happen spontaneously. It's a little bit like doing a business deal, right? So if you own a property and you're trying to lease it, you're not going to invest a lot of money in that property and redo the wiring and the plumbing and upgrade the landscaping and everything if you can't rent it for enough to offset the cost, right? There's no point in doing that. So the hybridization only will happen if there's a payback in energy when that bond forms. What we're going to do is we're going to look at hybridization of the interior atoms, and we're going to assume that terminal atoms are unhybridized. This is not exactly true, but it's a simplification that at this level we can easily do, and it won't cause us any problems. Yes?
And what do you mean by terminal atoms?
A terminal atom is one that's only bonded, that only has one bond, only bonded to one other atom. So when we draw the Lewis structures, it's the ones on the outside. If the atom is bonded to 2 or more other atoms, it's considered an interior atom. And those ones that form more bonds are more likely to hybridize. Yes?
So in carbon monoxide are both terminal atoms? Or
The oxygens are both terminal atoms in carbon dioxide.
carbon monoxide?
Oh, carbon monoxide. We're not going to look at diatomic molecules.
Okay.
Yeah. Because that would be tricky then, wouldn't it? Yeah, I almost skipped that. Did I skip anything else? Okay. So when you hybridize orbitals, you're taking standard orbitals, and think of it as putting them into a blender and then pouring them into a mold, and you're making new orbitals. You're changing them. You're mixing them up. The number of orbitals you end up with is the same as the number of orbitals you started with. They're just going to have different shapes and energies. What those shapes and energies are depend on the shapes and energies of the ones that you started with. The particular type of hybridization that occurs is one that gives the lowest overall energy. Okay, so that involves a lot of calculation. You have to try different combinations and see which one gave the lowest energy for that particular bond. We're not going to do those types of calculations. So what we're going to do is we're going to use Vesper theory and the electron geometries we learned how to read from the Lewis structures to predict the hybridization. Okay, so I did this lecture and worksheet yesterday, and people were like, well, but why is it that hybridization? Well, it's the lowest energy, but how do we tell? Well, it would be a lot of math. So what we're doing is we're looking at the Vesper theory, the number of electron groups, and it's the number of electron groups around that central atom that's going to tell us what the hybridization is. That is not why they are that hybridization, but it's a method where we can predict what the hybridization is without doing a boatload of math. So let's look at hybridization. So here is an energy orbital diagram for carbon. And here are the valence orbitals. Okay? And so we've got 2s and 2p. And the valence electrons for carbon, there are 2 in this s orbital, and each of these 2p orbitals has 1 electron, and then there's 1 empty. So hybridization is going to take all of these and hybridize them. That means that they're all going to end up being the same energy. So just like these 3p electrons, no, not electrons, 3p orbitals are all the same energy, they are the same shape. What's different about them? Are they right on top of each other? No. They're different orientations in space, right? One on the x-axis, one on the y-axis, one on the z-axis. 3 things perpendicular to each other. These are degenerate orbitals. When we hybridize these, we're going to have 4 now degenerate orbitals. They're all going to have the same shape, the same energy, but they're going to be oriented in space differently, just like the p orbitals were. So these are 4 degenerate orbitals. We call these sp3 hybrids because they're a hybrid of 1s and 3p orbitals. Okay, so sp3 means we took the s and all 3 of the p orbitals and we hybridized them. Okay, any questions?
What shape?
We'll get to the shape.
So for this, now that you just said that there's the 3 above the P, is there technically like an invisible 1 above the S because there's only 1 of those? Does that make sense then? So
That doesn't make sense.
So then why is there a 3 above the P for the sp3?
Because there were 3p orbitals. There's only 1 s.
No matter what, you're going to have 1 S.
Okay.
So it's,
And chemists don't like to write the number 1, so we don't say S1P3.
Okay, that's
Yeah. Here's the shapes. So what we're doing is we're taking the s orbital, which is a sphere, and these 3 different p orbitals that are just oriented differently in space. And essentially we're averaging them. Okay, it's difficult to visualize how averaging these would result in this. But people smarter than me have done the math, and I believe them. So this is what these orbitals look like. So now they're looking more like a turkey drumstick or something, right? Instead of 2 balloons together, we have a big lobe on one side, a small lobe on the other side. This allows the atom to overlap this orbital with another atom on this side with more overlap than just using one of these. Because here, half of the electron density is on the wrong side. And so it can't overlap as well. Here, we're concentrating electron density on one side of the atom, and it maximizes the overlap. So we have 4 degenerate shapes. The difference is orientation in space. How do 4 things get away from each other? Tetrahedron. So these 4 hybrid orbitals are going to orient in a tetrahedral shape. Now, in this illustration, we are not showing the little small lobe that's on the back side, because it makes the picture really complicated and hard to look at. We just have to realize, yeah, there is that little lobe on the other side. We're just going to ignore it. Okay, any questions? So if we hybridize those orbitals for carbon, we get now 4 sp3 orbitals. We started with 1 s and 3 p. We started with 4 orbitals, and we still have 4 orbitals, but now they're all the same. Carbon has 4 valence electrons. And so Hund's rule says that we're going to fill these with 1 electron first, and they're all going to have parallel spins. We're not going to put 2 of them together, right? The quantum hotel, the people take their own beds before they share, right? So what we've done is we've taken the S room with its 3 beds, and the S room with its 1 bed, and the P room with its 3 beds, and we knocked down the wall, and now there's 4 beds, and they're all the same. So 4 people coming in, they're each going to take their own bed. The geometry is tetrahedral. Now, each of these hybrid orbitals can overlap with the half-filled s orbital of 1 hydrogen atom. Now, our valence bond theory is predicting that we'll get CH4 and that the bond angles will be 109.5 degrees. And that matches up with observation. A theory is no good if it doesn't match with what we observe experimentally. Any questions? Yes?
So if you can't observe it, then you would have no way of knowing if it's a hybrid or not.
Well, if you can't observe the molecule, if you can't determine its geometry and its formula, chemical formula, then you can't tell if the theory is working or not. But this is working for most of the things. Valence bond theory doesn't explain everything, but it explains a lot more than VSEPR theory does. Hybrid orbitals can handle lone pairs. So ammonia does a sp3 hybridization, and so it'll make these 4 sp3 orbitals. In ammonia, we know that we've got N, here's the Lewis structure, NH3, and a lone pair. And so each of these hydrogen atoms is going to overlap its 1s orbital with the hybrid orbital on the nitrogen. And then this other orbital is going to have a lone pair in it. So if we look, oops, wrong tool. We look at the orbital diagram for nitrogen, this is 2s and 2p. It's got 5 valence electrons, 1, 2, 3, 4, 5. When we hybridize, we get 4 equivalent orbitals, sp3. 1, 2, 3, 4, 5. These 3 orbitals are the ones overlapping with hydrogen. They're half filled. This orbital has a lone pair in it. You might look at this and say, well, this predicts NH3 also, but it predicts the wrong bond angles. If these are unhybridized p orbitals overlapping with the hydrogens, the bond angles are going to be 90 degrees, and that's not what we see. The bond angle here is going to be, it's 107. It's less than the perfect 109.5 for a tetrahedron. But the way that valence bond theory explains it is a little different than the way VSEPR theory explains it. VSEPR theory says, well, the lone pair is more repulsive, or the lone pair takes up more space, and that squishes the others together. Valence bond theory says that the hybridization of these orbitals is less complete because of the lone pair. So they're not completely hybridized. This one has a little more p character than the others do, and so that's why the angle is different. Okay, so the unhybridized p orbital bond angle would be a 90-degree angle, and the observed 107 is a little closer to the 90 because of the incomplete hybridization. We're not going to make a big deal out of that, but I know some of you are going to wonder about it. Any questions? Well, there's different combinations that we can make with the hybridized orbital. We just looked at sp3. We can also make sp2, where we take the s orbital and two p orbitals and hybridize those. So starting with 3 orbitals, we're going to end up with 3 orbitals. The s orbital is lower in energy than the p orbitals are, and so the hybrid ends up being between them in energy, right? So we're going to end up with 3 sp2 hybrid orbitals because they have an s and 2 p orbitals hybridized together. So we'll get these, and then this one wasn't included in the hybridization, so it's just still sitting there as a regular old p orbital. And this is what that would look like, an s and 2 p orbitals. Again, we're going to get this kind of drumstick shape, but now we have 3 of them, and how do 3 things get away from each other in 3-dimensional space? Trigonal planar. And so these are going to form a trigonal planar shape. Where's the 3rd p orbital? Well, we're not even talking about what electrons are in there right now. If we hybridized this x and the y p orbitals, the one that's left is z, and z is going to be perpendicular. So one lobe is going to be sticking out at us, and the other lobe is going to be behind this. So there's an unhybridized p orbital that's still there. It's just not shown in the picture. Yes?
Why was it left unhybridized?
We'll get to the reason why it was left unhybridized. For now, we'll just say, well, we're going to look at all the combinations, and then I'll explain why. So if we look at H2CO, this has sp2 hybrid orbitals. So here are the orbital diagrams for the valence electrons of the atoms involved: hydrogen, oxygen, and carbon. Carbon is going to hybridize the s and 2 of the p orbitals, and we're going to get this sp2. So we've got 3 sp2 orbitals, and we have 1 unhybridized p orbital. And so these 4 electrons are going to fill up, not fill, they're going to half fill each of the sp2 orbitals. And then this guy, this is a little hard to explain. Why is he up there instead of pairing up here? The difference between the sp2 energy and the p energy is not that great. So the difference between s and p was this difference. Between the sp2 and the p, the difference is smaller. And so in the quantum hotel, that electron says, well, it's going to cost me 50 cents more a night to go into that p room by myself and have my own bed. That's worth it. And so that the 4th electron is actually going to go over here. We're assuming that the hydrogen and the oxygen, being terminal atoms, are not hybridized. And so we see this oxygen, and here it's got a half-filled p orbital, and that can overlap with one of these sp2 orbitals. And this has 2 hydrogens. Each hydrogen will overlap with one of these. And then we'll talk about what happens to the unhybridized p orbital. So here isn't that a pretty picture? Glad I didn't have to draw that. So this green thing is intended to represent a horizontal plane, okay? So here are the purple hybrid orbitals. So sp2, it's got this trigonal planar shape. One orbital overlaps with hydrogen. This orbital overlaps with that hydrogen. This orbital overlaps with one of those unhybridized p orbitals on the oxygen. That carbon had an unhybridized p orbital that had an electron in it. And that orbital is going to be perpendicular to this trigonal planar of the hybrid orbitals. Does that make sense? So this is half-filled, and oxygen also has a half-filled p orbital. And so that's sticking up here, and these can overlap side to side and form the second bond. If we look at the Lewis structure for this molecule, that's the Lewis structure. We're not going to worry about the two lone pairs on the oxygen. These are the two lone pairs. We're assuming this doesn't hybridize, and so those are just an unhybridized p orbital with a lone pair, unhybridized s orbital with a lone pair. We're not going to draw them on the picture because isn't it complicated enough? When we get too many things overlapping, it's hard to see. So we're going to be ignoring the lone pair on the oxygen right now. But this orbital overlaps in a side-to-side fashion with the p orbital on the carbon. Yes?
Can we just assume that terminal ones are never going to be hybridized?
That's what we're assuming. That's exactly what we're assuming. It's not true, but it doesn't mess us up. Any other questions? So these orbitals, the sp2 and the p orbital from oxygen, are overlapping end to end. These unhybridized p orbitals are overlapping side to side. This is one orbital, this part and this part. That's one orbital. And this is one orbital. And they overlap on both of their lobes. That's one bond. Do you think this is weaker or stronger than this end-to-end overlap? Weaker. Because there's strain involved. The overlap is not as good. They're kind of stretching out to reach each other, whereas these guys are just overlapping very nicely. This is going to be a much better bond. This is like gluing paper flat side to flat side, and this is more like gluing paper on the little skinny edges. You could do it, but it's not going to stick as well. So this is called a sigma bond, and these are called pi bonds. Okay, so sigma, I just blanked on that. The pi, the way you remember that, the pi bond is perpendicular, and the sigma bond, it was an S word. Is it symmetrical? It's on the worksheet. Can't remember it now. But the sigma bond is end to end. The pi bond is side to side. So pi bond overlaps side by side. What's important to remember is that the electrons occupy both lobes. And that was one of the kind of confusing things about those quantum mechanical orbitals, right? It's like, well, there's the nucleus, and here's this region of probability here and a region of probability here. So how can the electron be here and then go there without going through the nucleus? That's where thinking of electrons as waves makes it a little easier. Because you remember the video I showed you with the string? With a standing wave, right? Kind of looks like a p orbital. So here's one end of the string, here's the other end of the string. And the string is going up and down. There's a blur here and a blur here, but this point in the middle where there's a node doesn't move at all. The wave is on both sides of the node, and yet it's not in the node. So think of these orbitals as being standing waves of the electron as a wave. When we take these two and interact them, they will form an interaction like this. And so there's a pair of electrons in here, and just like this one electron is on both sides, the pair of electrons is also on both sides. It's just a funky combination of standing waves. You can't really visualize, you just have to say, okay, well, smarter people than me figured that out. We'll just go with that. End to end is a little easier to understand. So this half-filled p orbital, that half-filled p orbital overlapped, and this is what's called a sigma bond. It's symmetrical. Okay, so S sigma for symmetrical. This is symmetrical about this axis, and the p bond is perpendicular to the bond axis. We can label each of the bonds in this molecule, and this is something you'll need to do on the worksheet. We're going to label the type of bond, whether it's sigma or pi, and identify the orbitals on each of the atoms that are overlapping. When we look at the bond here between the hydrogen and the carbon, the s orbitals can only form sigma bonds. They can't do that side-to-side overlap because they're a sphere. So this is going to have to be a sigma bond, and it's an overlap between the carbon's sp2 hybridized orbital with the hydrogen's s orbital. Okay, so that's the notation. This is not a minus sign, it's a dash. So sp2 on the carbon, dash, so s on the hydrogen. So that's this one. This bond is the same thing. The same type of orbital on the carbon, the same type of orbital on the hydrogen. This one in the middle is end-to-end overlap. It's symmetrical, and so we have an S, it's a sigma, sorry, S for symmetrical. Sigma is the Greek letter S. The other thing I like about sigma is it looks like a circle, right? And this is like a circle. So we've got a sigma bond, and on the carbon, we have an sp2 bond. So that's what this is telling us. On the oxygen, we have a p orbital. It's not an sp2 bond. It's an sp2 orbital. So we've got the p orbital on the oxygen overlapping with the sp2 on the carbon. You okay? Because if you're not getting it right now, this is a great time to ask questions. This bond, this and this is one bond. This is a pi bond because we have side-to-side overlap. And we have an overlap between a p orbital on the carbon and a p orbital on the oxygen. And so these are the types of labels that you're going to need to put on your worksheet. You have to label each type of bond.
And it says bond description.
Bond description. Mm-hmm. So that's the bond description. Any questions? Yes?
So the sp2, that is how does the p2, where is that in the diagram?
Well, if we have S and two P's, that's 3 orbitals, right? So it makes 3 hybrid orbitals, and so that's where we get these purple ones. That's why there's 3 of them, and they're making a trigonal planar shape. If they weren't hybridized, we'd have a spherical s orbital, and we'd have those p orbitals at right angles to each other. Okay? Any other questions? So we get more insight from the valence bond theory than we do from the Lewis model. The double bond between the carbon and oxygen there is 2 different kinds of bonds. Lewis theory doesn't tell us that, but valence bond theory shows us that. A double bond in the Lewis model, you know, if you draw the Lewis structure and you have a double bond, that's always going to end up being 1 sigma and 1 pi bond in valence bond theory. And a triple bond would be 1 sigma and 2 pi bonds, and we'll see how that works. Those pi bonds are generally weaker, and we see that experimentally. You can do reactions where you break one of the bonds and not the other. That happens a lot in organic chemistry. It's the pi bond that breaks. The sigma bond is stronger. It takes more to break that one. Another thing that we observe experimentally is that single bonds can rotate and double bonds cannot. get my little models here. So in this illustration, we have two similar molecules. This is 1,2-dichloroethane. This is 1,2-dichloroethene. The difference here is that this one has a single bond between the carbons, and this one has a double bond. The reason that this one has 2 more hydrogens is we have to fill out those valence octets, right? So in this molecule, you have a sigma bond here between those are labeled wrong.
That's what I was thinking, should be
Huh.
SP3.
Let's fix that. I didn't notice that yesterday or any of the other times I've taught this. I hate it when the book makes mistakes. This one is actually chlorine, and this one, so this is chlorine, and that's actually a P. And over here we have C, SP3.
And why is that?
Well, here we have 4 orbitals, hybrid orbitals. We're going to get to how you would predict that. From the picture, we can tell they're hybrid orbitals because they're purple, right? There's 4 of them. To get 4 orbitals, you have to have the S and the 3 of the P's. So these are SP3 hybrid orbitals, and they're oriented in a tetrahedron. This bond is the end-to-end overlap of an SP3 on this carbon with an SP3 on that carbon. Here we have SP3 on the carbon overlapping with a P bond on the chlorine, and these are SP3 on the carbon overlapping with an S orbital on the hydrogen. And these are the same types of bonds. This you can rotate. So let me show you what that looks like. Didn't have this quite right. Having to destroy my acetic acid to make my 1,2-dichloroethane. Okay, so this is the molecule. You got carbon with single bond, 2 hydrogens on each carbon, 2 chlorines on each carbon. It can rotate. So you can have 1 chlorine up and 1 chlorine down. It can just spin around, and it does. When you put a double bond in there, that pi bond overlaps above and below. With that double bond, you can't rotate it. And so you're going to be stuck with the chlorines on one side. If you want to rotate it, you have to break bonds. Yeah, that's easier said than done. It's easier to do it this way. You can't just rotate it like you can with the first one. There, now I've got 1 chlorine up and 1 down. And that double bond doesn't rotate because of this overlap that's perpendicular. These p orbitals don't swing around on the nucleus. They retain their orientation. And so in order to spin this end, like I did over here, you're going to have to break that bond. Okay? Single bonds rotate freely. Double bonds do not rotate. Here are space-filling models illustrating this. This model looks different than that model, right? But they're actually models of the same thing. Because there's a single bond between the 2 carbon atoms, this can rotate. It can spin around, and so it's actually just the same molecule. That's like, a person sitting down or a person standing up. Are they 2 different things? No, they just bent over when they sat down and then they straightened up when they stood up, right? You can do that. The double bond, you don't have that rotation. So it's stuck like this. The 2 chlorines can be on the same side. In organic chemistry, we call that cis. or they can be on opposite sides, and that's called trans. You don't have to remember that, but it can be on opposite sides. But these are two different molecules. They have different physical properties and different chemical properties. They're similar, but they're different enough that you can separate them, and they will react differently in chemical reactions. These are just exactly the same molecule standing up or sitting down, basically.
So is that what you're talking about when the Lewis structure doesn't tell us these things?
The Lewis structure does not predict this. We know it happens by experimental observation. Lewis bond theory helps us understand why. And a good theory does that. It says why. So that's the double bonds. We can also form triple bonds. And so this is a different hybridization here, sp. So now we're taking the s and a p orbital and hybridizing these. We get two degenerate orbitals, same shape, same energy. And this is called sp because there's an s and a p. And then what remains is two unhybridized p orbitals. Well, how do two things get away from each other in three-dimensional space? Linear. They go to opposite sides, right? We take this and we average it with that. Now this is a little easier to visualize. We're going to end up with these two things. Again, looking like the drumsticks. So one is pointing this way, one is pointing the other way. When we draw them together, it's simpler to just ignore the small lobe. And so it looks like that. That looks a lot like a p orbital, doesn't it? But it's fatter, and it's not the same. It's actually two orbitals. This little lobe is kind of inside of that other one, and this little lobe is in here. And that's not the case in a p orbital. P orbital has one lobe on each side, and they're equal in size. So let's look at the Lewis structure for acetylene, which is remarkably similar to that. So that's the Lewis structure for acetylene. Acetylene has sp hybrid orbitals. So this is the orbital diagram for carbon's valence electrons. This is the hybrid orbital diagram for carbon's electrons. So we've taken an s and a p and hybridized them. So we have these two. They're going to each have one electron in them. And then here we have the unhybridized p orbitals. Again, think of it as the energy difference between these two is small enough that it's better for these electrons to be alone in their orbital rather than having to pair up. Because I can certainly understand why you might want to put both of these over here, because you said fill up the lower energy orbitals first, right? I did say that. But here, they are close enough in energy that it's more important for them to have their own space. So this shows us that each of these carbons can form 4 bonds. So this is what acetylene looks like. It looks like some crazy balloon sculpture, doesn't it? So this is one sp orbital, hybrid orbital for carbon. This is the other one. And this carbon also has an sp and an sp. One of these sps is overlapping with hydrogen. That's this single bond out here. And over here, one is overlapping with hydrogen. That's this bond out here. We also have one bond between the carbon that is the end-to-end overlap of the sp hybrid orbitals. Those are all sigma bonds, end-to-end overlap. But there were 2 unhybridized p orbitals that were half filled. So one of them is up and down on this carbon and up and down on that carbon, and so they can overlap side to side. So that's a pi bond between the p orbital on one carbon and a p orbital on another carbon. So this hybrid orbital used the x p orbital, and this is the y p orbital, and then both of these also have the z orbital left. And so that's going to stick out this way and overlap in the front and behind and form another pi bond. And those 3 bonds is the triple bond between the carbons. I think that's really cool. Yes?
So you said we can't tell the sigma bond between the two carbons just by looking at the Lewis structure?
Well, I'm going to show you how to predict the hybridization by looking at the Lewis structure, but we haven't gotten to that quite yet. Yes?
I'm confused why there's four of the long pi orbitals.
Okay, so this, it looks like there's 4 bonds there, doesn't it? There's only 2. Because the p orbital, maybe I'll make this red, keep with the color coding. So on carbon, the p orbital is shaped like that. That's 1 orbital. Okay? Both sides is 1 orbital.
Okay, I got you. So it's really 2 and then the...
It's just that the, yeah. So, and here's 1 orbital on the other. And they overlap side to side like that. That's 1 bond, 2 electrons. And then the other one is perpendicular.
Can we go more into the describing part, the bond description?
This part?
Pi and sigma? Yeah.
Yeah. So a pi bond is the side-to-side overlap. And we're really only going to see that in the p orbitals. So if you have p orbitals, they're going to be pi bonds overlapping side to side. Those are going to be the second or third bond of a double and triple bond. The first one's always sigma. The sigma bond, end-to-end overlap, those are going to be the hybridized orbitals. Those will overlap end-to-end. The pi bonds will form between unhybridized p orbitals. So when you look at the Lewis structure, and all of this is going to start by looking at the Lewis structure. If you only have single bonds, you're only going to have sigma bonds. If you have double bonds or triple bonds, the double bond is 1 sigma and 1 pi. The triple is 1 sigma and 2 pi. Okay? And so, because you can't have another bond, another sigma bond between these 2 atoms, because there's not another orbital that's right on top of the first orbital. The orbitals have their own space. Any other questions?
I don't understand the red part.
This part?
Yeah.
Okay, so we've got the 1 orbital on 1 atom and another orbital on the other atom, and each of them has 1 electron in it, right? And so the bond is the overlap of 2 half-filled electrons, 2 half-filled orbitals. The end-to-end overlap is pretty easy to understand. These guys can't overlap end-to-end because they're standing up next to each other. And so the best they can do, think of it maybe as 2 people. Let's make the person black. Think of it maybe this way, as this is a person, and here's a person, and they can't get any closer together, so they overlap by holding hands out to each other, and then they're going to stick their legs out to each other. I'm all for crazy analogies, if it helps to make any sense of it.
So are there 4 people? Or are there just...
This is, one pi bond is 2 people, 2 orbitals. Where the orbital is the person. The top and the bottom here are 1 orbital. And that's what makes it a little tricky, because we look at these purple ones and it's like, well, that's only 1 lobe, because the other lobe is small and insignificant and gets confusing when we draw it. But they actually do have, this, here's this SP, SP orbital. It also has a little lobe over there. And this one has a little lobe over there. It just gets really confusing when we draw those small lobes. The small lobes do not overlap with each other.
I think it'd be helpful if you drew the people on the diagram that's up.
On here?
Yeah.
Okay, I can do that. So here's 1 orbital, 1 p orbital, and here's another p orbital. And they're saying, hey, I want to hold on to you. I'm going to stick my foot out, and we're going to lock feet. Play footsie, maybe.
Shouldn't they be laying down right there?
They can't lay down. These guys are laying down. They're kissing. How's that? These guys are kissing. That's better, that's stronger. These guys are standing up, but they can't get any closer because those guys are laying down between them kissing? I don't know.
But if they're going, if the orbitals are going horizontal,
Mm-hmm.
why wouldn't the people be, like, see how you drew it on the right side?
Well, by putting their arms out, they're stretching out more of their mass between them.
So that's their overlap.
That's the overlap. They can't overlap as well as these guys, right? They just can't overlap as well. They're doing the best they can. And, you know, people don't bend in the right directions for this to work all that well. But. Oh, maybe this would be better. Let me try something. So, this might be harder to draw. I'm going to go back to the double bond, because maybe that'll be easier to draw on. So here we had a, oh, that's not the best one.
So we're not going to be drawing that, right?
You're not going to have to draw this.
Okay.
No. Okay, so let's look at this pi bond and try to explain it. So now what I'm thinking is I am making this up on the spot here. So this is the top of one guy's head, and this is the top of the other p orbital's head. And they're sticking their arms out, and they're holding hands. Geometrically, I think that works a little better. So I'm sticking my arms out and holding hands. It's me on both sides. There's two of us, one on that side, one on this side, and we're holding hands. We have some overlap, but that's not as good as this overlap in the middle.
So in the business inside your show, there are two people, but there's four.
There's one person here, and there's one person here making this pi bond. And there's one person here and one person there making this pi bond. So there are a total of 4 orbitals, 2 on each atom, that are involved in that. Let's do this. So, you know, my stylus is dying. So the carbon's hybrid orbitals, we've got the sp and we've got the p. Whoops. And they each have 1 electron in them. And here's the other carbon with the same hybridization. So this carbon, oh, let's put the hydrogens in there too, might as well. Here's the other hydrogen.
So those are not the hybridized.
The hydrogens do not hybridize. Okay, so the carbon shares one of its sp orbitals with hydrogen. Okay? And the other carbon shares one of its sp hybrid orbitals with the hydrogen. That's this bond right here. And this one right here. And then it's got 3 more. It's going to share the sp of one carbon with the sp of the other carbon. Those are going to overlap head to head, end to end. And then a p will overlap with a p, and a p will overlap with a p. Those are perpendicular, and they can only overlap side to side. Keep asking questions till it starts to make sense.
Okay, so you're talking about the P ones, those are the guys that are standing, right? with the men?
Yeah, the p orbitals are holding hands on either side of this people who are making out in the middle, I guess.
And the SP is the purple.
Yes, the hybridized orbitals in your book are purple. P orbitals are red, s orbitals are blue. Why? I don't know. Yes?
You never have a pi bond by itself without that sigma.
You can't have a pi bond without the sigma. That's correct. The strongest bond is going to form first. Okay? And so the sigma bond will form. The pi bond is kind of the leftover. It's weaker. And so if you just had a pi bond, it's just not going to, it just wouldn't work. The molecule wouldn't stay together. Yes?
So you're saying from the orbital, the one from the top and the bottom, it forms perpendicular.
Yeah. And so this is the hands, maybe the right hand of this guy, and this is the left hand with the right hand of the other. That didn't help at all. So we've got one here, and they're holding hands across this way. And then the other two are perpendicular and holding hands here and here. So you're holding hands on both sides. That's one bond.
So we're going to draw the orbitals?
You do not have to draw these things.
Okay.
Aren't you happy about that?
So then, like on the worksheet, how would you find out that stuff if you don't have a picture?
We're getting to that. Okay, let's go on here. So that's not all. In the Lewis model, we talked about expanded octets and how elements in the third period can expand their octets and have 10 or 12 electrons, right? In valence bond theory, this involves hybridization, including the d orbitals. The energies of the d orbitals are similar to those of 3s and 3p. They're different, but they're in the same neighborhood, right? On the hotel, those were on the same floor. So you can, knock down walls and hybridize and join these things together. So you can hybridize the s and the p's, and then if you need more, you can go up and grab one of the d's. Now those d orbitals are empty, right? Because if you have your valence electrons in 3s and or 3p, there's nothing in the 3d yet because those don't fill up until after the 4s fills. So these are just sitting there empty, but we can borrow one of them. So hybridizing these will get us 5 hybrid orbitals. They'll be degenerate. We're not going to really look at the shapes. I think you've got the idea. You've got 5 things shaped like purple turkey drumsticks, and they make a trigonal bipyramid shape. So these are the 5 hybridized orbitals, and then those unhybridized d orbitals are still just kind of sitting there. So here is arsenic pentafluoride. It has 5 single bonds to fluorine. And so arsenic will do this sp3d hybridized orbital, which gives us 5 hybrid orbitals in that trigonal bipyramid shape, and they'll each form a sigma bond with a p orbital from fluorine. So let's look at the orbital diagrams real quick, because this is the kind of thing you have to do on the worksheet. And again, you're just doing valence electrons. So fluorine has its valence electrons in the 2s and 2p. Right? It's got 1, 2, 3, 4, 5, 6, 7. So it has one half-filled orbital that it can overlap. And so that's what we're seeing here, is that p orbital on the fluorine. For arsenic is in period 4, and so its valence electrons are 4s2, 4p3. So 4s and 4p. 1, 2, 3, 4, 5. Looking at the atomic orbitals, we would predict that arsenic's going to make 3 bonds. But here it's making 5. What's going to happen is that there's also, didn't leave enough room, there's also this empty 4d sublevel. So what we're going to get here is we're going to take all of these and make hybrid orbitals. So you're going to get 5, and that's sp3d. And now you've got your 1, 2, 3, 4, 5 electrons, and they'll go 1, 2, 3, 4, 5. 5 half-filled orbitals. They can each overlap with a fluorine atom, and it'll have a trigonal bipyramid shape.
Can you have sp3d2?
Yep.
And keep going all the way up to 5?
We're just going to go up to D2.
Okay.
So would that, if it was sp3d2, would that just mean that the first 2 boxes of that one are filled, like completed?
If it was sp3d2, there'd be another box,
Why?
because there has to be 6 boxes.
Or D2?
For D2, because it's 2 Ds and 3 Ps and an S, that adds up to 6 boxes. But let's wait till the next slide for that. So this is the sp3d2. So the S, 3 Ps and 2 Ds. 1, 2, 3, 4, 5, 6. 6 orbitals hybridize, you get 6 orbitals out. They just changed in shape, and now they're all the same energy and all the same shape. And so those make an octahedron. And those other d orbitals are just left unhybridized. And I know it's really bugging you guys. Why is it sp3d2? We'll get there. We'll get there. So here's an example of that. Sulfur hexafluoride. So it does the sp3d2 hybridization. It gets 6 equivalent hybridized orbitals. They arrange themselves in an octahedron, and then each of them can form a sigma bond with 1 fluorine. And this agrees with the molecular shape that we looked at when we were talking about Vesper theory. Mm-hmm. A sigma bond. A sigma bond is the end-to-end overlap. The pi bond is that confusing holding hands thing.
So one of the ones in sulfur has the 2 electron in the p orbital has the 2 electrons spinning opposite ways, since it has 4 in the. There's 4 electrons in the p orbital, right?
Yes.
So
Electrons can flip their spin.
okay, so
They can change. Their spin can change.
Gotcha.
Yeah.
It was-
So yeah, in the atom, there was a pair with 1 up and 1 down, and then we draw the hybridized orbitals, and we're showing them all spin up. And what happened to the one that was upside down? That's what you're asking, right?
Mhm.
It just flipped.
Okay, so they just fills up.
They
one
can
of
do
those-
that.
Goes half into one of the d orbitals
Mhm.
or something.
And what we say is when they fill degenerate orbitals, 1 in each, they're always parallel.
Okay.
Okay, we know that. We can't say they're always positive or always negative. They're one or the other. By convention, we decide that they're going to be positive first and then negative.
So I kind of get where, like this, for the sigma, and then it has the sp3d2.
Mhm.
Why is it just a p for the?
Because the fluorine is not hybridized.
Okay, because it's on the outside, right?
Yeah, we're assuming it's not hybridized. So we're just going with the atomic orbitals from the fluorine, and we see that there's a p orbital here that's half full. So it can overlap that with one of these. So here we get to that question. How do we know? How are you knowing which hybridization to use for these different ones? Well, the rigorous method is the degree and the type of hybridization, because not all the hybridizations are complete. We saw that with the lone pair, is calculated to give the lowest energy to the molecule. Okay, that's very, very involved. We're not going to do that. We're going to go with good enough for Chem 1A, right? You don't always have to do the best, most perfect thing, right? So we're going to go with good enough. We're going to assign the hybridization scheme based on the geometry of the interior atoms. So we're going to look at the Lewis structure and count the electron groups, and that's going to tell us what the hybridization is. Not 100% accurate, but it's good enough, okay? So here's a table, which, you know, is nice for showing you, but we don't actually need to refer to this all the time. This is the place where it's really inconvenient being left-handed. So I'm writing on the fingers of my left hand, and my right hand does not know how to make letters.
I know that name.
And I feel silly asking someone else to write on my fingers, so I just do it myself. Okay, so you're doing this based on the number of electron groups. So if there's 2 electron groups, 1, 2, the hybridization is sp. If there's 3 electron groups, spp, sp2, Okay, because that gives you 3 hybrid orbitals that are equivalent. If there's 4, S, P, 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 sp3, okay? I don't have 6 fingers, so I don't go with the D thing, but you get the idea now, right? So 5, sp3d. You start with the S, you add as many of the P's as you need. There's only 3 of them. If you need more, then you go into the D orbitals. That's why the period 2 elements cannot do expanded octets. There are no 2D orbitals for them to borrow. They would have to go up to the 3s, and that energy jump is too big. It's not going to happen. In the quantum hotel, hybridizing orbitals amounts to renovating and knocking down walls between rooms. Okay? It's really hard to combine 2 rooms when they're on different floors of the hotel. You just can't do that. So I need a room that has 4 beds in it. I'm going to take the S room and the P room, and I'm going to knock down the wall. And now I've got the 3 P beds and the 1 S bed, right? And if I need more, I'm going to knock down another wall and steal 2 of the beds from the D room, okay? So, set of instructions for writing the Lewis, writing hybridization and bonding schemes. We start with the Lewis structure. You look at the Lewis structure and use the ideas we learned in Vesper theory to identify the electron geometry. The number of electron groups. Remember, an electron group is a lone pair, a single bond, a double bond, a triple bond, or a lone electron in a radical. Then you're going to select the correct hybridization for the interior atom. That's based on the electron geometry. You can look at table 10.3, but it's really not that hard. You need to learn how to do it without that. And I've had students ask me, can I write SPPP on my fingers during an exam? I'm like, sure. I prefer that you do it after you come into the exam, but I'm not going to check your fingers before you come in. But it's just really useful. How many do I need? I need 3. Oh, SP2, there it is. Yes?
Could we get the orbitals like tattooed on the back of our hand?
I suppose if someone goes to the effort and expense and pain of actually tattooing things on their body, I guess that wouldn't be considered cheating. Personally, I wouldn't tattoo a crib sheet on my hand just to pass Chem 1A. It's just not that important.
Okay, it's useless. You're like, oh.
Yeah, I just wouldn't recommend it. And then sketch the molecule, okay? You're not going to be required to sketch the molecule on the worksheet. But at least when you're getting started on a piece of scratch paper, try to sketch it out so that you can see what's going on, what kind of overlap you're getting. After you've done it a couple of times, then you can see it in your head. It's much easier to draw things in your mind than on actual paper, isn't it? So sketch it and show the overlap using the appropriate orbitals on the terminal atoms. The orbitals on the terminal atoms are going to be the half-filled orbitals in their just regular electron configuration. And then labeling them. We label them sigma or pi. Sigma is the end-to-end. Pi is the side-to-side overlap. Followed by the type of overlapping orbitals. So the element symbol, and then in parentheses, the type of orbital, and a dash, the other element symbol, and the type of orbital.
I'm sorry to go back to this, but
That's
how do you
okay.
get the 2 leftover p orbitals?
Well, you hybridize the S and one of the P's, and then the other 2 are just sitting there not doing anything. They don't get changed by that.
So that's just if you had let's say
It's an Amber
sorry,
Alert.
I'm trying to
Everybody's phone's probably going off.
Yep.
It's an Amber Alert. Yeah.
distract me. I don't want to.
I know, right?
Sold that. California. Or sold that.
Hmm?
They're kind of ironic. It's happening. Sold dad, California.
Soul dad.
Sold
Single dad.
Someone's missing.
Okay, let's just do an example. That's okay. Write a hybridization and bonding scheme for xenon tetrafluoride. Let's start with the Lewis structure. So let's put a xenon and put the fluorines around it. It's important to finish the Lewis structure because the lone pairs are sometimes really, really important. So how many electrons are in this molecule? Valence electrons. 36, yeah. There's 8 from the xenon. There's 4 fluorines, they each have 7. And so that adds up to 36. So I've already got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, bless you, 26, 28, 30, 32. I have 4 more electrons. They go on the xenon. Xenon's a big boy. He can expand his octet. So I'll stick 2 there, maybe I'll stick 2 over there. It doesn't matter exactly where you stick them. They're on the xenon. So there's our Lewis structure. Now we ask ourselves, how many electron groups on the central atom? 6. 4 bonds and 2 lone pairs. So we have 6 electron groups.
Wait, how is it 6 electrons? So 4 bonds and
2 lone pairs
around the xenon.
on the xenon.
Okay.
So 6 electron groups, that means when I hybridize my orbitals, I need 6. So I got 1, 2, 3, 4, ran out of fingers. I should write them on my other hand, but then I'd have to go like this. Then you go into the D's, right? So sp3d2. That's the hybridization. This comes from the number of electron groups. The number of electron groups comes from the correct Lewis structure. Everybody okay with that? So I've got S, and there's 3 P's. That only gives me 4. I need 6, so I have to use 2 of the D's. We're not going to go higher than 6 electron groups. They're uncommon if they exist. So that's the hybridization. What's the bonding going to look like? Well, I think it's a good idea to draw it. I'm going to draw it. So here's the xenon in the middle. And let's use purple because these are hybrid orbitals. So hybridized orbitals, there's 6 of them. That's going to make an octahedron, right? And so I've got 1 hybrid orbital up there and 1 down here, and I have 1 kind of coming out at us and 1 kind of going back, 1 coming out and 1 going back. Looks like a mess. Looks like a droopy flower.
That's an octahedron, like a pyramid.
Yeah, it is an octahedron, and here, this is the plane sticking out, and then we've got up and down. And so, what are these orbitals going to overlap with on the fluorine? Well, you might need to look at the valence electrons for fluorine. It's got 2s and 2p. It's got 7 valence electrons, right? 1, 2, 3, 4, 5, 6, 7. So this is the half-filled orbital that's going to overlap with the xenons. So I'm going to have a fluorine here. Oh, but wait. There's 4 fluorines. There's 2 lone pairs. We need to think about where the 2 lone pairs go. Let's put 1 lone pair down here. If the 1 lone pair is down there, where's the other lone pair going to be? On the other side. Okay? So we're going to put the other lone pair up here.
And those are the ones that are surrounding the xenon, right?
The purple ones are surrounding the xenon.
No, I mean like those lone pairs that you just put on the up and down.
Right, they're in the xenon's hybrid orbitals.
And you got that from the Lewis structure, the ones that are attached to the xenon?
It has nothing to do with this.
Where'd you get the sp3d2 thing?
I got the sp3d2 from needing 6 hybrid orbitals. And to get 6, I need the s, 3 p's, and 2 d's. That adds up to 6 orbitals. If I want 6 hybrid orbitals, I have to start with 6 atomic orbitals and hybridize them.
Isn't there 2 S's?
There's only
One S box.
there's one s orbital that holds 2 electrons, but we're talking about boxes here. Okay, so over here is what xenon looked like. Xenon is period 5. So 5s and 5p. And it has 8 valence electrons. So we look at that and we think, why would that bond at all? Well, it doesn't really like to, but it will do some. What it'll do is, we know that it needs to be sp3d2. So that's, 6. 1, 2, 3, 4, 5, 6. So sp3d2. What happened to the other 3d orbitals? Nothing. They were empty before, and they're just sitting there empty. They're just not being used. It's okay.
What do you mean other 3D?
Because there's 5 d orbitals, we use 2.
So we used, oh, that's way too big. So these are the 5, level 5 d orbitals. And for the atom, they were empty. There wasn't anything in them. When I hybridized, though, I hijacked 2 of them. And so this is what I took to hybridize. Because I need 1, 2, 3, 4, 5, 6. So that I can get 6 that are the same in energy.
So, and that 6 is from the 6 electrons?
That's from the 6 electron groups around the xenon. Okay? See, this is good. You guys are asking questions. So we look at the Lewis structure. We see we have 6 electron groups. So that means we need to take 6 orbitals and hybridize them. 1, 2, 3, 4. Then we go to the Ds. 5, 6. So those 6 orbitals then get hybridized. So they're all the same energy, same shape, just oriented in space differently. We had 8 valence electrons. So how are those orbitals going to fill up? 1, 2, 3, 4, 5, 6, 7, 8.
Which we have 2 little pairs.
So this is a lone pair, and that's a lone pair. That's these guys. And we have 4 half-filled orbitals, and each of these is going to overlap with the p orbital on 1 fluorine.
Crazy multitasking.
Right? If you persist in working on this until it makes sense, it's crazy beautiful. I mean, it's just like, that is so cool.
Like a symphony.
Yeah, it's just harmony, and it just all comes together. It's awesome. Yes?
The fluorine, 3 boxes for the maybe fluorine.
I'm sorry, this is not, I was drawing, this is the fluorine that's up here. Yeah. So I was trying to do the orbitals. So this is a p orbital for fluorine that's overlapping with this sp3d2 orbital on the xenon.
Can you explain the concept again real quickly? When we circled in red 5s, 5p, 5p,
Mm-hmm.
how you're going lower into energy when you're going to sp3d2?
When you hybridize these orbitals, the hybrid orbitals are higher in energy than the lower ones, and a little lower in energy than the higher ones. It requires energy to do that. The energy payback comes from the stabilization due to the overlap with the orbitals on the other atoms. Did that answer your question? Any other questions? Yes.
So that fluorine bond right there is like a kissing one, right?
Yes, this is end-to-end overlap.
Whereas if it was xenon H4, it would be just kind of have a little bond.
Well, the s orbitals in hydrogen, that's also considered a sigma bond.
Yeah, it's still sigma bond. They're both sigma bonds. They just look differently.
They're just going to look a little different in how they overlap, but they're the same type of bond. We have two kinds. There's sigma and pi. And the pi only happens between the p orbitals.
Okay, so pi would be like if two of those fluorines joined together.
Possibly. If you look at the Lewis structure and there aren't any double bonds, there's no pi bonds.
Yeah. Okay.
And so we don't have any pi bonds on here because those only show up in double and triple bonds.
Gotcha.
The sigma bond is the one that forms first.
Could you get those schematics spin from
Up here? Okay, so
purple flower?
oh, so this is the electrons from this orbital, and this is that orbital. I put them in those particular places because we know that they're going to be opposite each other. I could have picked this one and this one, but then it's a little harder to draw and visualize. So if I'm going to continue drawing, I'm just going to start making the fluorines themselves red. We're going to have our 4 fluorines overlapping like this. And then the electrons, if you want to show the electrons, there's a pair of electrons, one from the fluorine, one from the xenon, in each of these bonds. So one fluorine overlaps its electron with one of these half-filled orbitals here. So that makes one bond. And then another fluorine does the same thing with another one, and so we have 4 of them. It's helpful to draw this picture when you need to go label the bonds. So these bonds are all essentially the same kind of bond, right? There's sigma. It's an end-to-end overlap. Maybe I'll make this blue. So these are sigma bonds, and it's a bond between xenon and fluorine. What orbital on xenon? There's not even close to enough room there. Start over.
So, will these just kind of be, I wouldn't say standardized, but like for the fluorine, would it always, because it always goes on fat a certain amount, because it has a specific amount of Valence electrons, it'll always be like what you're putting into here?
In this simplified treatment that we're doing, where we're assuming that the fluorine is not hybridizing at all, the fluorine's always going to make one bond, and it's going to be this p orbital that's going to overlap.
Okay.
So we're going to get this, we've got the p orbital on the fluorine, so we put a p over here, and the orbital that's overlapping on the xenon is the sp3d2 hybridized orbital. sp3d2. So in this description, we tell the type of bond, sigma or pi, and we show the 2 elements that this bond is between, and we show the hybrid orbital on the xenon and the unhybridized p orbital on the fluorine. When you have a double bond, you're going to have 2 descriptions, one for the sigma bond, one for the pi bond. In some molecules, you can have one kind of bond between nitrogen and an oxygen, and a slightly different bond between a nitrogen and a different oxygen. And so in this molecule, there are 4 bonds, and they're all the same kind of bond. But that's not always the case. Any questions? Let's do another example. Okay, I did this one yesterday for the other class, so you can watch the YouTube video. No, wait, I did CO2. Yeah, I did CO2. I did not do this one, so we're going to do this one. It was so long ago, right? It was yesterday. Okay, so what do we start with? Lewis structure. Okay, so we're going to have hydrogen and carbon and nitrogen, and we've got 1 electron, 1 valence electron from hydrogen, and 4 from carbon, and 5 from nitrogen, and that adds up to 10 electrons. So I've got 2, 4, 6, 8, 10. I ran out. What do we do?
Change it.
Move them, share more, make multiple bonds. So I'm going to take this lone pair and make it a bond.
We can't do the octet on N.
Well, you could take, whoops. I could take these electrons and stick them over here, but that's not good. Carbon's not happy. If we look at formal charges, things are just not good here. So I'm going to move, oh, I don't want to move that one. I'm going to move a lone pair and make it a bonding pair. Is this good?
Yeah.
No. So I need to do it again. I'm going to take another lone pair and make it a bonding pair. Is that good?
Yes.
Yeah. So if you evaluate the formal charges, they're all 0, and we've got octets except for hydrogen. He has his duet, and so everything's good. How many groups on the carbon? Electron groups?
No, 2.
2.
Because it's a triple.
Electron groups. A triple bond is one group. Okay, one group. So 2 electron groups. What's the hybridization?
SP.
SP. 2 electron groups. So we've got SP, hybridization,
Why is it? Oh, because.
because there's 2. 2 fingers, SP. Okay, so I'm going to go ahead and draw, because you're going to have to do this on the worksheet, and I think it's very helpful, looking at the valence electrons and their configurations. So here's the atom with its 4 valence electrons. When we hybridize that, we're going to take an S and a P and hybridize those together, and then we have p orbitals that are left. And so I'm going to put the 4 electrons, they're going to go in here like this. Again, the energy difference here is small enough that it's better for the electrons to have their own orbitals. In the quantum hotel, people would prefer to have their own bed, but if sharing a bed saves you $150 a night, you're going to do it, right? It's just not worth it. But what if it was $5 a night to get your own bed? You're like, yeah, the benefit outweighs the cost. So because these are close in energy, the benefit of them having their own orbital outweighs the energy cost of them being in a slightly higher energy. Yes?
So it's basically like you're taking a box from the P and putting it on S, right?
Yes.
And then you're evening it out.
Yeah, so the diagrams that were done earlier were like this, right? And so then we would be taking these 2, and we'd be hybridizing them, and we'd get 2 in the middle there, and then these P are the same. So these are the 2 that didn't get changed at all. When we take these 2 and average them, their energy comes to be in between. And that reduces the energy difference here, and so that's why it's okay for them to go up before pairing. Yes?
So kind of the whole point is you have them be equal when you hybridize them?
What you want, the goal, of course, we're just trying to describe what actually happens. But the goal in hybridizing is to end up with the number of hybrid orbitals that's equal to the number of electron groups. Okay? So because there are 2 electron groups, I'm going to take the S and only 1 P. If I need 4 electron groups, I need to take 4 orbitals and hybridize them. If I need 5, I've only got 4 with the P's and the S. I have to go up and take a D. Okay? So here's the hybrid orbital diagram. This is the kind of thing you write on the worksheet. And we're assuming that the nitrogen and the hydrogen do not hybridize. So the hydrogen's going to be easy. He's always just the same old boring thing. And the nitrogen, ooh, that's not a very good box. The nitrogens look like that. So each nitrogen has 2 electrons in its s valence orbital and 3 unpaired p orbital electrons, right? So we've got the carbon bonding with the hydrogen. So this is carbon. It can take one of its sp orbitals and overlap with the hydrogen. So I'm going to draw this down here. So here's carbon, and I'm going to draw its hybrid orbitals here. sp, there's 2 of them. They're going to go on opposite sides like that. And over here is the hydrogen. And the hydrogen has an s orbital, which is ending up being way too big, but that's okay. So this orbital here, is that sigma or pi? Sigma. So that's a sigma orbital between carbon. What kind of orbital on the carbon? sp. And it's with the hydrogen, and what kind of an orbital on the hydrogen? It's the s. So that's the description for this bond. And then we've got the nitrogen over here. We're assuming that nitrogen doesn't hybridize. This s orbital is full. That's going to be a lone pair. We're going to ignore that. Question?
So that's not sp2 right there?
This is sp2, the carbon. The carbon hybridizes to sp2, and then 2 unhybridized p orbitals are left.
Isn't that sp on the other side?
Did I say sp2?
Yeah.
I'm sorry. sp. It's sp. Because s and p is 2. Maybe that's where I got the 2. This is, I mean, you think listening to this is hard. I don't have a script. I didn't practice this. I'm just talking off the top of my head. It's amazing more garbage doesn't come out. sp, not sp2. This is sp. So on the nitrogen, the orbitals that are going to overlap are these half-filled p orbitals. So here's a p orbital overlapping with the carbon. How do we describe that bond?
Sigma.
It's a sigma. What kind of orbital on the carbon? sp. And what kind of orbital on the nitrogen? P. That's why the worksheet wants you to draw the orbital diagrams so that you can look and see what's overlapping. It's got to be something that's half full. So there's the sigma.
Can you explain more why it's just, I understand in the first sigma part why the hydrogen is just S, but why in the second one is the nitrogen just P?
Because we're assuming that it doesn't hybridize.
So then why are you leaving out the first box?
It's already
It's
filled.
full. This is a lone pair.
So you're writing the ones that are not.
Yeah, I mean, I can put it in here. So the nitrogen has an s orbital with a lone pair in it. That's this box right here. It's an s orbital with a lone pair in it.
And so the leftover gets put in the parentheses, right?
The half-filled orbitals are the ones that are going to overlap. Because you can only have 2 electrons in an orbital. And there's 2 electrons in a bond. The orbitals overlap. That's the sharing we talked about when we were talking about Lewis structure. Because now I'm overlapping my orbital with your orbital. And so those 2 electrons that are in there, now it seems like they belong to both of us. And that holds us together. So one of these p orbitals overlaps with an sp hybrid on the carbon. The s orbital on the hydrogen overlaps with a hybrid orbital on the carbon. And so that's what we've got here so far. And this is a lone pair. Let's put the electrons in there. And there's electrons in here. What about these orbitals and these orbitals? Well, look at the Lewis structure. There's a triple bond. we need to describe those. There's two more bonds. So this is where things get messy. So we've got an unhybridized orbital on the carbon and on the nitrogen. And those are going to overlap side to side. How do we describe that bond? It's a pi bond. I'm going to write it over here. It's a pi bond between what orbital on the carbon?
P.
A p. And on the nitrogen?
P.
P. So this is the description for this bond.
And it's like that because there's the P box left over on the nitrogen and the P box left
Right,
over
we've
on
got
the
P,
carbon.
P here, and P there. And so now we've got these guys overlapping. And then the other P orbitals are also going to overlap.
They're the ones that are holding it.
Well, these are holding hands too. So here you would be looking down at the tops of the heads. And here's the hands on one side and the hands on the other side. And then the other one is perpendicular. So there's another one that's coming out this way and overlapping. And that's the second pi bond. So we have two of these, and one of those, and one of those.
Oh, so you don't draw another pi.
Well, I don't need to do this again. You could say times 2. There's 2 of them. But the description is the same for both of these because it's an overlap between a p orbital on the carbon and a p orbital on the nitrogen, and it's a pi bond. So the description is the same. Any questions?
I just see that makes sense through the whole picture.
Good, good. And in a picture like that, if you just look at the finished product,
Doesn't make sense.
doesn't make any sense at all. Hopefully when you see it being created, it makes a little more sense. Okay?
Is there not necessarily an easier way, but a better way to do it without drawing the picture? Because the picture is what confused me more than anything.
You don't have to draw the picture. What you have to be able to do, though, is to look at these orbital diagrams and figure out how they're going to overlap. So the hybrid orbitals are always going to form sigma bonds. And so form those first. And so without drawing the horrible picture, I can look at this and say, well, there's got to be a sigma bond between carbon and hydrogen. If I look at my orbital diagrams, what on the hydrogen is half full? Well, it's the S. So it must be the S on the hydrogen, and then it's got to be one of the hybrid orbitals on the carbon, so it's going to be an sp. So that's going to be this one. In this triple bond, I have one sigma bond. That's going to be the hybrid orbital on that interior atom, and what's available on the other atom. On the nitrogen, the s orbital isn't available, so it's going to be a p orbital that overlaps. Hydrogen's actually the only one where I think we'll run into where it's overlapping in s.
So on the 2p for carbon, you said that there was 3 that were unpaired, so is that how you got how many electrons to put in the sp and the p?
So for nitrogen,
No, for carbon.
oh, for carbon. For carbon, I took, so you're okay with this, right? This is the atomic electron configuration or orbital diagram. I'm going to get to this place where I have 2 boxes and 2 boxes because I look at this and I see 2 electron groups. That tells me I need to take 2 of these orbitals and hybridize them. So I need 2 on my fingers, S, P. So an S and a P, and I hybridize those, and that's where I get this. And then what's left is these 2. So now I'm not going to really look at how the electrons were positioned here. I'm just looking at the number of them. There's 4 electrons here, and so I'm going to put them in singly. another hint that you need to do that instead of pairing these up is you have to have half-filled orbitals to make bonds. And I look at this and there's 4 bonds. There's 3 bonds here and there's 1 bond there. That means in my carbon I have to have 4 unpaired electrons. And so that's why I'm putting them like this. Does that answer your question? Any other questions?
Do the bonds tell you how many you need to have it?
The bonds tell me how many half-filled orbitals I have to have. And on the nitrogen, just nitrogen as its regular atom orbital diagram has 3 half-filled orbitals. And so that's why nitrogen tends to form 3 bonds. Yes?
And how do you know which one comes first when you're describing the sigma and the pi? Like for the first one on the worksheet, when it's the beryllium difluoride, then since there's 2 of the fluorines and 1 beryllium, but beryllium has less valence electrons, then how do you make the sp? Because there's 2 groups, so it'll be sp. So how do you?
It'll be sp, yeah.
So how do you make that though?
You take an S and a P and you hybridize them and you put the 2 electrons in there. We'll talk about that. Any other questions? Okay. I did that one yesterday, and I think your heads are probably full, and we've taken a long time, and so we're going to save this for next week, because this would make your heads explode.